Good evening. Uh, what I thought today was to discuss a little bit about Laplace transform and how to use Laplace transform techniques to analyze the RC circuits. And what we are going to discuss today directly is related with the task 1 of your project. So the circuits that I am going to discuss are pretty much closer but not the same as what you are supposed to analyze, but once you closely follow this, it should be easy task for you to do the analysis that is required in task 1. But on top of what I am going to discuss, you will also need to do a bit of research, maybe on the web or in wiki and so on. Then it shouldn't be a big problem for you to handle task 1. I'll use the screen capture as usual, so I'll stop this one and switch over to the screen capture now.
Okay, let us look at these couple of slides. I just named it as Laplace transform and analysis of RC circuits. First thing is, I just want to show you how to find out the voltage at this point, V out, if there is a network of resistors, just two resistors connected in series, and the one end of the network is connected to the ground, the other end is supplied with the time varying voltage of Vi, and we are interested in finding out what is the voltage at the midpoint V out, and there is no current taken out from that point. So just assume that we just hold the two probes of a multimeter to the ground and this point, and we want to monitor the voltage. And the problem is to find out mathematically what is V out in terms of the input signal R1 and R2. So then we know that V out, if the voltage at this point is V out, can be written as R2 times IT, because IT is the current going through R1 and R2 to the ground, starting from the supply voltage Vi. So V out T is R2 IT. That's the first equation. And also, if you start from the supply point, there are two resistors in series. The equivalent resistance is R1 plus R2, and the current going through R1 and R2 can also be written as IT is equal to VIT divided by R1 plus R2. So if you substitute from 1 in 2, you can write V out T as equal to R2 divided by R1 plus R2 times VIT. And then what this type of a circuit is doing is basically dividing the supply voltage according to the resistance ratio, because R2 divided by R1 plus R2 is the fraction we have here. So with that meaning, we call this kind of a circuit a simple potential divider circuit. So this is a very useful relationship which you can always apply in order to find out output equations for output signals when the input is given. And if you can identify this kind of a network in your circuit, you can always apply this relationship. This is a useful one. And then if you just consider a simple capacitor, charging of a capacitor, how to write the differential equations for that, that's also important. So here what we have is a capacitor with the capacitance of C. One end is supplied with a voltage of VIT, time varying voltage. The other end is connected to the ground, And if we assume that the charge in the capacitor is Q is equal to C times VIT. Q is equal to CV, charge is equal to the capacitance times the voltage, is a standard equation. And then if you think of the definition of the current is the rate of charge flow. Therefore, I can write IT as equal to dQ by dt, the derivative of the charge accumulated in the capacitor. Then I can integrate it. So I can write Q as equal to integral IT dt, which is the second relationship. Then using 1 and 2, I can write C times VIT is equal to integral IT dt. Therefore, VIT is 1 over C integral IT dt. So that's the simple relationship for the charging of a capacitor. Then let us consider this simple RC circuit, which is usually called as RC low pass filter circuit. The reason why it is called low pass filter we will take up after a couple of slides. So what you have here is a resistor connected in series with a capacitor. This point is supplied with the input voltage of VIT, and you take this point, the signal at this point is taken as the output, but remember we are not drawing any current from this point at the moment. Therefore, this current IT flows through the resistor, goes into the capacitor and to the ground. So if that is the case, the current can be always written as VIT minus VOUT divided by R, considering this branch. VIT minus VOUT divided by R. From the capacitor charging, I can also write, just like what we did in the last slide, VOUT is equal to 1 over C integral IT dt. And for IT, I can substitute from the previous equation. So I get 1 over C integral VIT minus VOUT divided by R dt. Therefore, cross multiplying will give me C VOUT is equal to integral VIT minus VOUT divided by R dt. And then if I differentiate this equation, I get C dVOUT by dt is equal to VIT minus VOUT divided by R. And again, if I cross multiply and rearrange the terms, I can write RC times dVOUT by dt plus VOUT is equal to VIT. So now if you look at this equation carefully, it is a first order differential equation. The dependent variable is VOUT and the independent variable is VIT. So VIT is the input signal, VOUT is the output signal. And then the differential equation has the circuit parameters. So now it is a question of how to solve this simple differential equation. So what we are going to do for that is to analyze it in S domain or in Laplace domain. So you should know, I mean, this is not electrical engineering, this is just pure mathematics after this. And given the first order differential equation, I'm sure you have learned how to get the Laplace transform of that differential equation. So this is the first order differential equation, RC dVOUT by dt plus VOUT is equal to VIT. Now we get the Laplace transform. Only thing, assumption that we have to make is assuming no initial charge in the capacitor or zero initial conditions, because you will remember that when you get the Laplace transform of the first derivative, you need the value of VOUT when t is equal to 0. So what we assume here is that that value is 0, so that you don't have to worry about V0 T0 minus that value, right? So that's 0. So because of that, I end up with RCS V out S plus V out S is equal to VIS. So now V out, capital V out and capital VI are in S domain, Laplace transformed variables. So then rearranging the terms will give me V out S is equal to 1 over RCS plus 1 times VIS. Or else, if I divide the numerator and the denominator from RC, I end up with V out S is equal to 1 over RC divided by S plus 1 over RC times VIS. And then, therefore, the transfer function, which is usually denoted by HS, or sometimes we use GS also, is the ratio of V out S and VIS. V out S divided by VIS is this much, 1 over RC divided by S plus 1 over RC. We will be touching upon these concepts of transfer function and so on during the lectures also a little later in the term. But for the time being, then the simple definition for the transfer function is, given a system, if the system is driven from a certain input and if there is an output, if you get the Laplace transform of the input signal and output signal with the system having 0 initial conditions, if there is no initial energy stored in the system, like in case of the capacitor, if the capacitor is initially uncharged, then we say capacitor, that system has 0 initial condition. So if the system is in 0 state or 0 initial conditions, if you get the Laplace transform of the input signal and the output signal, and if you get the ratio of that, that is called the transfer function. So what you are looking at here is the transfer function of the simple RC low pass filter. And then it is also important for us to be able to analyze and find out what is going to be the output signal for certain input signals which can be mathematically defined. So in most of the situations, the step, a signal like this, how a system or how a given circuit is going to respond to a signal like this is a very important thing, because if you think of just switching on of power to a motor or something, what you are doing is just applying a input signal having this shape. Let's say it's a DC motor, and then you want to switch on 110 volts DC across the armature terminals of that motor. So what you are effectively doing by pulling the lever of the on-off switch is applying a voltage signal to the terminals of that motor, which has this shape. So because of that, step signal is very important. And then this particular step signal is called a unit step because it has an amplitude of 1. Before t is equal to 0, it is 0, the value is 0, but after t is equal to 0, the value is 1. And then I'm sure you know that the Laplace transform of ut is 1 upon s. So if we are going to apply that signal to this RC low pass filter, this is what is happening. Your VIT will be now ut. So if we are doing the analysis in S domain, I can write V out S is equal to 1 over RC divided by S plus 1 over RC times VIS. And VIS is 1 over S because of this. So I substitute it here and then do a bit of simplification. Finally, if I get the partial fractions of this one, which again I am sure you should No, I can write 1 upon S minus 1 upon S plus 1 over RC is equal to V out S. So now it is a matter of getting the inverse transform, for which we usually use inverse transform tables, inverse Laplace transform tables. So then to find out the step response in time domain, I get the inverse transform V out t is equal to inverse Laplace transform of V out S, which is equal to inverse transform of 1 over S minus 1 over S plus 1 over RC. So that I can write as V out t is equal to ut minus e to the power minus t over RC times ut, that you get from the inverse Laplace transform tables. Now it is a matter of sketching this one to find out what type of a shape is it. So that can be done by using superposition. I can separately sketch this signal, separately sketch this one, add the two together to give the final sketch. So ut is a shape like this with an amplitude of 1. E to the power minus t over RC is a shape like this, starting from minus 1. Sorry, I have forgotten to put plus 1 and minus 1 here. When you add the two together, it is more like you are shifting this red curve up to this point, which is shown here. So it starts from 0, it exponentially rises and then asymptotically reach the value 1. So that is the shape of ut minus e to the power minus t over RC. And then, the value of the function when t is equal to CR is an important one. When t is equal to CR, remember CR is in the denominator of e minus t over RC, the exponent of E. So when t is equal to CR, what happens is V out t will become ut at t is equal to CR minus e to the power. Since the numerator is also assigned the value CR, the two CR terms will cancel out and e to the power minus 1 will remain. E to the power minus 1 times ut when t is equal to CR. So when t is greater than 0, you know that ut is always 1. So in places where ut is, I can just substitute 1, which means I end up with 1 minus 0.3697, which is approximately 0.63. So starting from 0, when time is CR, the output has now raised 63% of the final output value. So with that meaning, we call t is equal to CR, the value t is equal to CR as the 0 to 63% rise time. Since the signal is rising from 0 to its final value, we call it rise time. But in your real task, you will see fall time. So then I leave up to you to find out what should be the fall time and how to find that one. If you come all the way up to this point where you can sketch the output signal for the RC low high pass filter, then you should be able to figure out what should be the 0 to 63% fall time. So I'll leave it up to you. Then I also wanted to touch upon frequency response or the Bode plot. One thing I would suggest right now is for you to go to this link in Wiki, which gives a very nice description of Bode plot, and yeah, just spend a couple of minutes on that. That will give you a very good understanding of what is a Bode plot. That is easier than me explaining it remotely like this. and after that I'll leave you some time to do that, and then I will uh, restart to tell you how to create a Bode plot using MATLAB. Alright, I still would like to talk a little bit about the transfer function before I move on to MATLAB. Now if you look here, a transfer function typically is a ratio of two polynomials of S. That's S is the Laplace transform variable. Now in this case what you have is a very simple form of a transfer function, because if you look at the denominator, it is a polynomial in S, but it's a first order polynomial. And then in the numerator you just have the constant term, but there can be, in a more complicated transfer function, there can be higher order terms of S in the numerator as well as in the denominator. So now if I switch to MATLAB, let me just do it. Yeah, now if I switch to MATLAB, the way MATLAB handles a transfer function is like this. One has to define what are the coefficients of the numerator and denominator polynomial. Coefficients are these terms. What is the constant term and what is the coefficient of S? In this case it is 1, and so on. So you define the numerator and denominator polynomials of the transfer function. Now in this particular case, if you consider the first order low pass filter, I have assumed a resistance of 10 kilo ohms, R is equal to 10K, and a capacitor of let's see now, 1, 2, 3, 4, 5, 6 microfarad. So a resistance of 10 kilo ohms and a capacitance of 6 microfarad, and my numerator polynomial is just the constant, so it is 1 over R into C, and the denominator is 1 stands for the coefficient of S, which is 1, and the constant term is 1 over R into C. And then what we do is we define a system object. That is how MATLAB handles it. System object sys1 is equal to TF, stands for transfer function. Just type help TF in the command window, you will get what it is all about. So I'm not going to do that, it's up to you to do that research. So TF within brackets numerator num comma den, right? Numerator and the denominator. So when we come up to this point, we have defined the transfer function of the RC low pass filter in MATLAB. Then if I am interested in the step response, I can call a figure 1, and there is a command called step of sys1, that is the step of the system 1. So that will give me what is the step response of the system. So let us execute this and see whether we get the same output as the one we sketched. So before running it, I have to set the MATLAB path. So I go down my computer, D, probably this is the place. Yeah. I run this one. So as you can see, it starts from 0, goes up to 1, and then 0 to 63% rise time is somewhere here, which is around 0.01. T is equal to CR, and CR in this case is 1 upon, yeah, it is 1 upon CR is 100, therefore CR is 0.01. If you just need, if I add the grid on the figure, it will be more clear to you. Like if I, so at t is equal to 0.1, the value is exactly 0.63. So that is how get the step response of the system. And then in another figure, I can also get the body plot. Body plot is the frequency response plot. Frequency response, in other words, is how the system is going to respond. This network is going to respond if we apply sinusoidal signals of different frequencies as the input signal. Then certain signals will be sent without any attenuation, but certain signals will be attenuated. That depends on the frequency of the input signal. So low pass filter means low frequency signals will be sent through without any attenuation. High frequency signals will be attenuated. That's why we say low pass. The meaning is low frequency signals are passed through, whereas high frequency signals will be cut off or suppressed. So this is a very important circuit when you have situations where you need to cut off the unnecessary, unwanted high frequency noise components of a signal. Low pass filtering, and simple low pass filtering can be done from a simple RC filter like what we have been analyzing so far today. So if I execute the new the modified program now, you will get an idea about how the body plot looks like. So this is the body plot. Let me add the grid, and then so a typical body plot, it's up to you to read about the body plot and learn a little bit about it. Has a magnitude plot as well as a phase plot. So magnitude plot, as you can see, 0 decibels means there is no attenuation all the way up to somewhere here, and then the other signals are attenuated, high frequency signals are attenuated. And then phase also, there is more or less no phase delay in the signal in the beginning, but later on it keeps on adding phase delays up to 90 degrees to the output signal. So that's about the body. And with that, I'll again switch over to the PowerPoint and quickly show you how the design of this filter can be done. A quick one. Sorry. Now again, from the wiki link that I gave you, it is possible to read about the cutoff frequency. Cutoff frequency is the frequency from which those frequencies above the cutoff frequency, input frequencies above the cutoff frequency, will be suppressed, whereas the frequencies below the cutoff frequency will be passed through without any attenuation in case of a high pass filter. In case of a low pass filter. If it is a high pass filter, all the frequency components below the cutoff frequency will be suppressed, whereas frequency components above the cutoff frequency will be passed through without too much attenuation. So cutoff frequency is the place where the body plot starts bending. So just read a little bit more on the cutoff frequency, and then if we are to design a low pass filter for a given cutoff frequency, this is the procedure we follow. We know the relationship between the cutoff frequency and the circuit parameters R and C is this. Fc is equal to 1 upon 2 pi RC. So then if we are to design a low pass filter with a cutoff frequency of 1 kilohertz, this is what we can do. 1 over 2 pi RC is equal to 1000, which means RC is equal to 1 upon 2000 times pi. So we pick a capacitor. So I have asked, I think, to choose the capacitors and resistors from E12 range. Just do a web search. E12 range is the standard range. Those are the values of capacitors and resistors that are available in the market. So just pick, I just picked 100 nanofarad, right, for the capacitor. And then from this relationship, I can find out what should be the resistor. So then R is equal to 1 over 2000 pi into 100 into 10 to the power minus 9, that's 100 nanofarad. Simplifying that gives me R should be equal to 1591 ohms. Then I go back to the E12 range for the resistors, and the closest I can find from the E12 range is 1.5 kilo ohms. So I choose a 1.5 kilo ohm resistor for R. So as you can see, it is not exactly the designed value, but it will give reasonably good results in terms of signal suppression, high frequency noise suppression. So I think with that I'll wind up today's session. Now it is up to you to do your own research and find out corresponding details in case of a high pass filter. Do the Bode plot, try to do the Bode plot, try to do the design. So I have discussed all the basics that you need. So now I think you have enough knowledge to get on with task 1 of the project. Let us meet next week. If you have any problems, if you have kind of half done M files and so on, I will be more than happy to look at them. Just click me an email with the attachment. I can have a look at and comment. Or else we'll meet next Tuesday and discuss further. See you then. Bye.